probably seen pictures like this for the rotation of the sun, where it's slower at the poles and faster at the equator. But what we're missing is the idea that the sun is traveling in this direction. So to get actual space velocities, what you have to realize is that if the sun is traveling this way, this point, besides rotating, it's also traveling this way, and so on. So the actual velocity at any point on the sun's surface compared to space is this way, this way, this way, etc. And you get the idea. At the center of the sun, the velocity is this direction. As we move out, it rotates like that. Okay, here I just want to show you the difference between counter rotation and differential rotation in a Bessel function filament. Now you're familiar with this idea of a Bessel function filament. This will be a view coming towards you where the magnetic field is outwards, then downwards, inwards, upwards, outwards, etc. It rotates. So if you're in a large scale object with a filament like this, you will see counter rotation. But if you are small compared to the filament, right in here, you will see differential rotation. If the sun is in the middle of a large scale filament, the center of the sun traveling this way, as we move out and we just start getting that rotating magnetic field, we'll have faster and faster rotation out to this point. You get counter rotation if you have many of these layers. You get differential rotation between the center and the first azimuthal winding. That's the trick to putting the sun in that Bessel function filament, where Don Scott and Michael Claridge already have this correct picture of the sun traveling along a filament with the planets spiraling around the outside. Now I'd like to show you something that might matter for the solar cycle. As I've shown you, that if our sun is in a current filament with a magnetic field this way, and then it rotates more and more azimuthal out here, we can match the differential rotation of the sun to that current filament exactly. And we should have a minimum energy configuration sun, a nice quiet sun. But the problem is, if we move the sun side to side, and we know that there is a motion of the sun around the solar system barycenter, watch what happens. If the sun is still rotating in the same direction, but now it moves over to here, what should happen to charge moving around this way if the background magnetic field now is not aligned with the surface, but this direction? What should happen is we should have charge moving around, crossing a magnetic field, and therefore erupting out of the solar surface, and then spiraling around that magnetic field. But here's the twist. If we're really spiraling around that magnetic field for a solar arcade, as it moves out, as that solar arcade expands, it's going to see a twisting magnetic field, and then what should happen is the solar arcade itself, as it expands, it should twist. And we see that. That's why I believe that's not the dipole magnetic field of the sun that explains that. That can be explained by a rotating magnetic field outside of the sun. In other words, the current filament that contains the sun has to dominate even that close to the sun to give that twist to solar arcades that we see as they erupt from the solar surface. All of that happens very quick compared to the rotation of the sun anyhow, so we know it's not the sun's dipole spinning around that does that. That is just the effect of a solar arcade expanding into a rotating magnetic field. Okay, another idea I want to show you is that with the idea of our solar system being in a large-scale current filament, we have this idea of these cylinders of charged material that should be moving through the solar system. Well, here's something interesting to note, is that Venus is in a fairly circular orbit around the sun, and its spin axis is most up and down compared to orthogonal to that orbital plane. Now what we have for Earth and Mars is the orbits begin to get a little bit more elliptical. That is, compared to a circular orbit, they're closer to the sun on one side, I'll exaggerate this, and farther from the sun on the other side of the orbit. Well, what's interesting is that there's a close correspondence between the solstice points and the perihelion point, which just means that when the Earth is closest to the sun, that's at perihelion, that's very close to the winter solstice, which means Earth's north pole is tilted mostly away from the sun. And out here, it's the opposite. Earth's north pole is tilted towards the sun. And that's pretty close on December, winter solstice, early January for perihelion. So it's pretty close there. But you get the idea. If planets are actually getting their charge from these cylinders, when Earth is farthest out, its north pole is tilted towards that cylinder. When Earth is closest to the sun, Earth's north pole is still tilted towards that constant radius where all this charge should be flowing. And Mars is doing the same thing. It's not as obvious, but it's tilted the same way. That might be a pattern. It does make sense then for Venus staying in that cylinder and having an axis aligned with that cylinder. Planets like Earth and Mars, when they wobble in and out, will still try to keep the pole. If we're headed towards the north ecliptic pole, most of the current should be coming in that way, and then that would make sense.